Okay. Okay. And feel free to ask me question. Um, as usual, we are using the following sources. Primarily, I have taken it from Linux book by Robert Lau. This is possibly the best book available. Something I have taken from Linux book by Server and Koretsky. And then you can see one another book we have used today, which is by Richard Stevens and Stephen Rago actually, it's not Rogo, it's Rago. Okay, and this is a very good book. Actually, although little dated, but it's possibly one of the best books available on Unix. Uh, this book came sometimes around, I guess, around 20 years back, but still very good. Okay, you can read this from any source you want. Possibly, you may not have. Actually, you can download. Just a minute. Wow, you can buy this book. It's not very expensive. This book, anyway, you should have a Robert Love book. Okay, all right. Okay, so today we'll look at file system data structures, file system namespace, virtual file system, and file system API if time permits. We'll try to finish it in about 1 hour and 10 minutes, or maybe 10 minutes extra. Okay, this is what we have studied earlier. File system is implemented by operating system. Because the users can only give commands or some APIs, okay, which are converted into system calls, and then OS does everything. Okay, so applications may just know there exists a file. It can create a file, it can delete a file, it can do operations of file. Okay, and rest of the activity is handled by OS. Okay, so it means that file system deals with all this. How these files are structured, named, accessed, used, protected, implemented, and managed. And we have seen that files can be structured in many ways, and byte sequence is the one which most of the file system use today. Okay, so file we can visualize nothing but an array of bytes. And this is very simple concept, right? And it's very powerful because now file can contain anything. Okay, depending on the way an application can interpret it. Okay, so you can write an application and design your own file. Okay, and then operating system has nothing to do with it, like Linux, Unix, or even DOS or Windows. It will simply give you byte stream, and then it's left to you how to interpret this byte stream as a user process, right? And then we have seen this most powerful representation of file, which we call the regular files. It's nothing but there's a byte stream, and there's a concept of file position. This we have studied in the last class. Okay, last two classes rather. And then we have seen files are of different types, and file or can also be of type directory. A directory contains information about the files that it contains, okay, and corresponding inode number. Okay, all right, and we have seen in the last class we can use a command to print or to output all the file names of a directory and corresponding inode numbers. Then we have seen that directory is not always a tree. It can have DAG or cycle, directed a cyclic graph. Okay, because a file can be referenced from multiple directories. Okay, and that we call this is possible using two approaches, but using hard link, which is most commonly used, and second is soft link or symbolic link. Okay, All right, this is what we studied in the last class, right? Okay, I hope you understood it. Any question up to what we have studied? Simple? Okay, let's move ahead. Okay, so today we'll look at file system data structures. Basically, what are the data structures that are used in general in a file system? Now, different operating system may have different data structures, but we'll look at very generic concepts, right? Largely used in Linux and Unix. In fact, Linux and Unix may also vary a little bit, but the basic concept is the same. Basic architecture is the same. Okay. The first data structure we have seen is inode. Okay. File is a file has a lot of metadata. Okay, because file has to be created by somebody, so that user ID or process ID has to be there. Okay, then what time it is created, what kind of permission it has, right? Access permission, whether it's writable, readable, executable, what, and combination of these. Okay, and then we have seen it also, another metadata is number of link count. Basically, from how many places, how many directories it is being accessed. Okay, so ultimate file may be the same, but we can have multiple names for it and then in multiple directories, right? Or maybe in the same directory there can be two links or multiple links with the different names, right? Okay, all right. So all this data about the file is there in inode. So each inode also has a inode number. Okay, this number that we see in directory actually points to this data structure. Okay, and then apart from that, inode also contains links to various blocks in a disk. Okay, because a file not necessarily has got to be on contiguous blocks. Okay, so all this information, what all blocks are there in the file and what order, all this information is there in this part. There's a files location on the disk. Okay, something like this. This contains all the information that we have discussed here, and then these are the links. Okay, which is called direct block and indirect blocks. Indirect blocks will have two references. First reference to another table, and from there we can go to indirect blocks. Okay, basically you can increase the number of blocks in a file by this method. Otherwise, the number of entries will really go up. If you represent in this way direct blocks, the number of entries will go up, and this file table will this inode will become large in size. That's the reason we have table of table, right? Same thing that we have seen in case of page tables. Similar idea was used. All right. Okay, and then we have seen this structure wherein we have directory entry which gives inode number, and this inode points to an entry in inode table. Okay, and this inode table okay contains the data about or this or metadata and file locations about that inode. Okay, and from this file location or metadata location of various blocks, we can get required block when we do reading or writing. Okay, any question? All right. Now this is what we didn't study in the last class. Okay. Now let's look at further down, right? In the sense that when we open a file, okay, what are we doing by opening a file? First thing is that all permission, etc. are checked. Suppose a process wants to open a file. First, while opening a file, the kernel will check whether user process has permission rights for doing that. Okay, and if so, then it opens a file, and by doing so, it creates various data structures. Okay, and initializes the file pointer, or the file position to the beginning byte, first byte. Okay, so the different data structures are as follows. Now, file descriptor comes to the process that wants to open a file. So because the process has to mention a file name, as a result of that, when kernel opens a file, finds out the file on the disk, and as a result of that, it creates multiple data structures, right? So and it returns a file descriptor. This is an integer number. Okay, we have seen 0 and 1 are file descriptor corresponding to standard input output or something like that, and third is for error, 0 1 2, and all other files that are opened will have subsequent file number file descriptors. Okay, all right. Okay, and from file descriptors, once this file descriptor, note that this is usually a process wide. Okay, it means that a process may open multiple files, or process may open same file multiple times, or combination of the both. So nobody stops you from opening a file 5 times, and for each opening you will get different file descriptor. Now you understand why we need file descriptor at user level. Okay, now when you open it, let's assume for 5 times, each time when it opens, the file position is in the beginning, but for each corresponding to each opening, you can manipulate in different ways. First, after some operation, the file position or the position may be at certain place, while second opening of the same file by the same process, the this file position could be somewhere else, and so on, right? So now multiple processes can open a file, and the same process open a file multiple times. But for each one of these, file descriptor is different because it gives information about that opening or that connection. We call it connection. And now we can understand that connection is different from each file. This is an instance of opening of a file. Okay. All right. Any question?
So just confirming that file descriptors at a point of time would be unique for a file for each file you have opened.
Not each file opening or each connection. It unique in the sense that, well, I mean, at each connection it's unique.
Yeah.
Okay, so it means that in system wide, this is system wide table, this descriptor has to be unique such that it can be used an index. Okay. All right, now does it mean that you cannot share a file descriptor with another process? Suppose two processes want to share a file, say for example a log file. Okay, then same descriptor can be shared by a process that has opened a file, created and opened a file to another process. Nobody stops from doing that, right? Okay. All right. So now there are various combinations. Same file descriptor can be shared by multiple process. and same file can be opened multiple times in a process and by multiple processes. All right. Now for each one of these, for each opening, there is a connection which for corresponding to each connection we have a file descriptor. All right, good, fine. Now this is a pointer to a system wide file table. Okay, fine. So now it means that now this table, this entry here should contain file position where this pointer is, for this, because a linear array and keeps moving. So this position should be also part of this. All right. Okay. And then, and some few other information this entry should contain. And this in general will point to, now we know where we are, exactly which byte we are doing operation on, but where all that is, because that corresponds to a file, and there has to be a inode which will contain many more information about the file, right? Okay. Now note that inode does not contain information about connections. It may have information about how many connections are opened, etc., but not more than that. All right. So inode contains information about all about the file, the ownership, the security, and the size, and other things, right? And where all things are, right? So all these things that are here. Mode, file mode, user ID, time created, and when last time updated, a location on the disk. All right. Any question? Now this system-wide inode table, this is a terminology used in Unix. In Linux, I'm sorry, this is used in Linux, and Unix we call it vnode table, which we'll see just in subsequent slides. Now I have a question to you. Where all these file descriptors corresponding to a process are kept? What data structure keeps this? And we have studied this.
Sir, in process control block in form
Yes,
of directories.
yes, that's right. Which we call it a process table also. Okay, corresponding to each process is a process table. Each entry will contain process control block. So PCB will contain all this file description. Very good. So this is the diagram that we have for single process. Okay, here two files are open. Of course, 0 and 1 we know, uh, standard IO. Okay, but in general, just look at this diagram. Okay, this PCB, this is nothing but a PCB for a process. So it, a PCB contains these two information, the file pointer. Okay, this is okay. So this will point to a file table. Okay, file table is nothing but system wide this table. Okay, all right. All right. So basically, look at the file descriptor. File descriptor is available to user process. It uses the file descriptor to look at or to index this table which is in PCB. Okay, and then this gives a pointer to a system wide index in system wide file table, which contains information about all open connections in the system that is being used by file system. Okay, so this table here, the table here contains all the connections. Okay, and this is one of the connection. one of the entries here that we have shown. So it contains file status flag and then current file offset. Okay, offset is nothing but position of which byte we are operating on, where the pointer is, current pointer is. What we call is file position or something like that, right? This one, file position. Okay, so that's important information, right? Okay, and it also gives pointer to a table which contains information about all inodes, which we call Linux, we call it vnode. In Unix, we call it vnode table entry, vnode table. Okay, so vnode table contains information. Note that this is all in RAM. Okay, so it contains information about each of the file, vnode of each file that is in use. Okay, it may not contain information about all the files that exist on hard disk. It's meaningless, right? So it's only those which are in use are brought in. When is it to be brought in? When file is opened. Okay, now this vnode table entry of course contains data about inode data basically. Okay, it contains information about basically inode information is kept here. Now note that when the use is over, a file is closed, then inode information is lost, right? It means that inode information, and that information about the file must be there all the time file is in existent in hard disk. Is that right? Okay, so it means that inode actually must be there in hard disk, and when file is opened it is brought into this table which is called inode table or vnode table. Okay, all right, any question? So basically all we are trying to see that what are different data structures that come into picture when we are trying to do a file operation. Okay, Tanuja, any doubt you have?
No, sir.
Okay, please feel free to ask me. I tried to bring in as much pictorial pictures from whatever sources so that flow becomes clear. Okay, all right, so now let's look at the next data structure. Now what we are doing here, now we are telling that two processes are using same open file. So ultimately each, this is process 1, this is process 2, the PCB contains all this information, all this table corresponding to different file descriptor, and then we can see file descriptor 3 here is pointing to a file table entry which is a global system wide file table. Okay, and here file descriptor here points to different entry. Okay, both are using the same file, yet different processor are using and different, there are two openings of that file, so both are pointing to different entries here. However, we can see that there's a v node pointer which is nothing but inode pointer which is pointing to same inode entry. Okay, also same vnode entry in global vnode table. Okay, all right, and then from here information can be brought in from hard disk. Simple. Now let's look at the big picture overall. This of course this diagram I have taken from a website, so it's not very, may not be very clean, but that's fine. But that's the only way, that's the only thing I could find out. Okay, so user space a process opens a file, it is given a file descriptor. The process ID, for example, is 1421. Then note that this field file descriptor is integer. It's given file descriptor 4, and then second process 1215 opens a file, okay, and file descriptor is given as 7. Okay, all right. So now in process table, you can see this process table has multiple of PCBs. Okay, this is PCB corresponding to 1215, and then we can see file descriptor 4 here gives a pointer to open file table. Okay, because note that this is just a, this will just give us a pointer. Okay, file descriptor just is an integer, so it has to point to somewhere, right? Okay, so now this open file table contains all the file descriptors corresponding to open connections, right? So now we can see that here it will give important one. Of course, there are status and other information. Important one here is offset, the file position. Okay, and it also gives pointer to corresponding information or inode information in vnode table. Okay, and then there is a reference count here is 1. It means that only one hard link exists. All right. Okay, although it's not necessary here. So now note here in vnode, this corresponding data corresponding to inode of a file. Which file? It will correspond to a file corresponding to this one, file descriptor 7. Okay, so now we can see that, okay, now this file is also, note that this file is also being used by this process in 1421. Okay, 1421 has two instances, basically two file descriptors is using, and this file descriptor shown here is pointing to details here. Okay, and then it points to same vnode. So the reference count you can see, it means that there are two hard links, one from here and second from the here, so it's 2. Okay, so now here corresponding to this one here, this instance is of course not shown, but something corresponding to here, we can see this is details of, you know, that connection. So it will tell us offset and other numbers, and then it points to different vnode entry that's corresponding to a different inode. Okay, any question? Are you able to understand the flow?
Yes, sir.
Okay, view it this way, that each file has all the metadata, file size, etc., and so on, and where it's located in inode. Okay, and it is there in hard disk. Okay, but accessing from hard disk is difficult. When file is opened, it's brought into main memory. So it means that all this information should be kept in some data structure, and that we call is vnode table. Okay, from hard disk you bring it here. Okay, when file is open. Okay, now any reference when you use when you do read and write, syscall from a process, then we have to use the file descriptor. Okay, and then when we use file descriptor, then there has to be information what we are trying to do on a file. At certain position we are doing reading. Okay, some number of bytes we are reading. That position etc. information is there in this open file table. Okay, and then okay, and so use of these two, vnode table, open file table, and file descriptor, which is in PCB, combinedly we can do file access. Okay. Now a question I am asking is that this ref count here, why can't we do it here in this one, open file table? Open file table also has ref count, but the global ref count cannot be in this table because this corresponds to, of course, an instance of process being opened, or sorry, instance of file being opened, right? So we cannot keep this because there can be many such connections from anywhere. Any process can open it up, right? So ultimately at the last node, which is vnode table, we will have to keep the global count. How many hard connections, hard links are there? Okay, if the file is being deleted, if this number is after decrement does not become 0, then file is not to be deleted, only link is to be removed. That we discussed in the last class. Now you can see the connection. Why do we need this count? Okay, all right. So now let's okay, all right. The last thing here says then in physical drive, what are we going to have? Now we also will have inode here information. All right. Okay, which will bring it to this place at the time file is opened. So now let's go through the details. Kernel and user process refer to each open connection by a number, which is called file descriptor. So when a file is opened, a file descriptor is given. Okay, multiple times a process opens a file, multiple file descriptors it gets. The kernel uses file descriptor to perform file operations. Okay, because all the places and the exercise you have done, you have used file descriptors. Okay. Okay, the kernel uses file descriptor to index one process file descriptor table, okay, which is nothing but PCB. Okay, a PCB may contains multiple file descriptors based, okay, and then you will index that, and from that we'll get a pointer to system wide file table. So this file descriptor table resides in PCB. All right, that we have already studied. Okay, all right. So now system wide file table that we have seen, which contains information about each connection. Okay, it keeps track of each connection of a file. Okay, and multiple files. Okay, okay, same file may have many open connections that we already studied, and distinct process may even share a connection. Fine, so file descriptor can be shared by multiple processes. Okay, all right, and connection information cannot be kept inside a process table. We have already discussed the reason why it has to be at the end. Okay, a kernel keeps data structures called open, okay, file table, which has entry for each connection. Fine, all this we have studied. Okay, so last one is open. This is open file table or file table. Okay, for each connection. All right. Okay, and then it contains entry to vnode. So here we have seen that contain is basically points to a entry in vnode table, or which has information about inode. All right. Okay, all this we have already discussed. All right. Okay. Any question? All right. So all this we have studied. Now let's look at. We have already studied regular files and directories. And when we'll study IO, we will come up with this concept called character special files and block special files. Okay, so why do we need special files? See, when we say file or a regular file, something that comes to mind is always a disk where you store, Word file or text file or JPEG file or whatever, MP4 file and so on. And files are usually reside in non-volatile medium, whether disk or flash or whatever. Okay, and we have seen that operation to file is open, close, seek, read, write, and so on. All right, can we use this abstraction of file for doing operations on various devices? Why can't we, a user process, consider a device, say for example a keyboard, as a file? So this file, from keyboard, the letters that are being typed can go to a buffer, which you can treat as a file, and then these characters can be read using read system call. Similarly, when we are sending data to a printer, we can write into a file, and then that file is printed onto a printer. Okay, now this file concept is when we generate here, but note that we need help of some device specific software, because when you say read or write, this is very generic, happening from top. Okay, but every device is different. There are thousands of printers there, right? And many printers are different. All these printers are different from each other. Okay, then we need a device driver. Okay, some other software, right? So that we'll study later. But in general, we can view the kernel objects as file. So Linux supports 4 types of files that we have. Special file that we call it. It's a block device file or character device file, named pipes and Unix domain sockets. We have already studied. Okay, you have done also an exercise on this one, named pipes. So the special files are the way to let certain abstractions fit into the file system. Kind of everything is a file paradigm. Okay. So now IO devices can be treated as a special file called device files. Okay, printer can be treated as a file, keyboard can be treated as file, mouse can be treated as a file. Okay. Now we are assuming we are viewing this device as a file, then device access can be performed through these files, device files, right? So they act like, to user, they, while user may give whatever command, but they are actually treated as a file, simple plain file, and at certain level where details of device are required, then special software is required. Okay. So the same system calls are used to interact with the regular file on disk. So the system calls that are used for reading and writing a file on a disk can be used to interact with IO devices. So hence device files can be opened, read from, or written to. All right. So now we can see that there are two types of files here: character device files and block devices file. Where okay, devices where we read byte by byte, okay, are character device files. Okay, so character devices are accessed as a linear queue of bytes, and device driver places bytes into queue one by one. Okay, so basically like keyboard or mouse or printer come into this category. Okay, other type is block devices file, where block devices are accessed as an array of bytes. Okay, so and then we can do seeking here. While here we don't do seeking, it's just linear queue. One after other, these bytes are available. Like when you're reading it from a keyboard, you cannot say I will read the fourth character first and then first character that's typed later. Okay, so you can read byte 12, byte 7, byte 15 and all that. And usually these are block oriented, right? Because blocks are minimum information that can be read or written into a disk. Okay, when the transfer happens, it happens in terms of blocks. Okay, so these files which are associated with the block devices are called like hard disk or CD-ROM drive or flash memory, etc. Use this kind of file, which is block device files. All right. All right. Any question?
No, sir.
All right. Okay, so now let's get into another concept called namespace. Have you come across this terminology?
I don't think so. No, we haven't.
Yes, sir. We have come like in while accessing files in C++. We use
Okay.
namespace. And,
Okay. So what is the namespace in general?
uh, like to map to access features from somewhere, we provide a namespace. Like we can access libraries of C++ as cin using namespace of std.
Okay. All right. Okay. This concept is very generic, very generic, right? I mean, when you use containers, etc., I'm not sure virtualization will cover, but then namespace become very important. Okay. So in general, namespace you can think as, for example, in your family, let's assume that your family starts with your father and all your mother and siblings. Okay, the name here and is unique, right? Okay, very unlikely you will have same name as your father's name. Very unlikely. Okay, because each entity has to be uniquely addressed or named. Okay, so namespace for your family is this. Okay, while namespace for your uncle's family is different, and that namespace can have, suppose your name is say Rohan. Your cousin can also have name Rohan. Okay, while namespace for your grandfather could be very different. Now that if you want namespace for your uniqueness in the that namespace, then you'll have to do something about it. Okay, so now let's look at namespace for a flash drive that you have. Okay, so how you are going to access that? All right, for example, in earlier times, say 20 years back, each I was not able to access the whatever drive, floppy drive, etc., as part of main file system. The namespace for that was different. It is called A drive, and then within that you can access it. It's not part of the global file system. So a process may want to read a file on a floppy drive. It was not possible. Okay, now, so earlier operating system had separate namespaces, like for disk drives and so on. So these were independent namespaces, right? So on a floppy disk, we were able to access using A. A was in general name for floppy disk drive. Okay, hard disk was located in C drive. And earlier DOS and Windows, I don't know about Windows 11 now, but they used to break the file name space up to drive letters. Windows 7 at least, I have used that time it was there. Okay. However, Linux, we have global and unified namespace of files and directories. So for example, now instead of telling a dot whatever, right, jpeg, we can now have a global way of addressing it using this path name /media/floppy/lang.jpg. So it's not a separate namespace like it used to be earlier. Okay. All right. Now the question is, then you have come across this word called mounting a file. Mount and unmount, right? You would have come across. Now when you attach your flash drive in your system, right? What does it do? It attaches it in at certain point in your directory structure. Okay. So now file system, a file system, for example, is something that is flash drive, or it could be of any type, right? We have discussed earlier there can be many different types of file systems, like FAT that was used in DOS, and Unix based file system, or even Apple based file system, or so it could be any file system. So file system, if or a directory containing the files, for example flash, can be individually added or removed from global namespace of files and directories. So your system has a global namespace, and if you attach a flash drive, it will now become part of that global namespace. So this operation of attaching it is called mounting, and unlinking it or detaching it is called unmounting. Okay, and but you will see that if this is a root directory and then it goes like this something that you attach as a flash drive will get attached at a certain point, say for example here. Okay, and if this is attached here, then you will have a directory corresponding to this, or maybe just number of files. Okay, so this point is called mount point. So CD, for example, you have CD drive, and CD might be mounted at /media.cd-rom. All right. So now let's take a simple example here. Before that, please go through this. I will not repeat it. So this is a USB volume. Okay, and then now we are attaching it to a file system. Okay, so this is a global namespace. So this is a mount point here, this one. Okay, so now once you attach it, okay, then then this thing will become part of this directory, LSS directory, right? Or you can attach in Bob's desk. You cannot similarly do attach here. Okay, so for example, now if Bob wants to access this file, okay, location.movie, then it can access using the path, this path /media/ okay, so it is here /media/ disk1. Now this is at mount point, and then /movies, then this one, right? So basically you just join these two, and that's called mounting. Okay, any question? All right. Okay, now let's look at what is a virtual file system. See, note that there are various file systems. Okay, various kind of file system, and file systems are also evolving. I mean, latest release of Mac OS has a totally new, a very new file system. Windows 11 has come out with modified file system. Okay, now the file systems are in order, or they are upcoming, right? New file systems are coming. So does it mean that I have a flash drive, or I have a, for example, a flash stick or memory stick with some file system, I cannot attach it to my system, which has different file system, because if I'm using Linux, it has different file system, right? So now to overcome that, Linux has proposed that let's define a global file system such that whatever be underneath file systems, but users will have a common interface for accessing them. Okay, so we have this system wherein user is giving, for example, copy command from one to another, and they may be part of different file systems. Okay, this may have one file system, another file system, and you're copying a file from, say, CD-ROM, DVD to hard disk. It should be possible. So there can be any file system, but at the user level, it will have same interface. So it will hide or abstract away differences between different file systems. Okay. So the application can access different file system on different media. Why? Via a homogeneous set of Unix system calls. All right. So now user can use this system calls like open, read, write to write in one of in write in, or read or write or do operation or files which may reside into any file system or any medium, on any medium. Okay, so now there has to be some glue or software which will hide all the differences. Okay, all right. Okay, so this will enable same system call to work between different file systems on different medium. In older system, this was not possible, right? In DOS system, if you somehow get hold of DOS, old DOS system, this was not at all possible, right? So now we have a generic interface, and that's possible by having an abstraction layer. around low level interfaces. Okay, so which can hide out all differences between different file systems like FAT, NTFS, or Unix and Linux have their own file systems. Okay, so now a user can use the same system call as we discussed earlier. The write, for example, FD is file descriptor, and into write data which is there in the buffer, okay, in the position given by FD, and this data length is given by LEN. All right. So now all this, so user space will use just simple call like this. The virtual file system will look at the the file system and use a corresponding system call. Okay, view it differently. That user, for example, is using very simple API. VFS will change it to, it will get kernel will change it to corresponding system call, syswrite, and then this syswrite will be implemented using some abstraction layer into very specific file systems write method. Okay, now whatever be here, whatever file system, this system call given to user remains the same. All right, this API that user uses remains the same. All right, this is the basic concept of virtual file system. So we are not going to go into details of this. I just want to bring it to discussion because I felt that you should know this. This is a very important Linux and Unix concept. I'm sure Windows must also be doing similar stuff, in some way or other. Okay, any question? All right. Then let's go into the last part of discussion today, which is basic file system APIs. You know all this, so we'll finish it next few minutes. Okay, creating a file. Now, when we say API, we are not talking about system call. These APIs are available to users in general for doing operations, and we'll get into details in subsequent classes. Okay, so basically a library that's in user space provides these APIs. Okay, now for each API there must be some syscall that you can look at, and we will actually get into that little later. But in general, you can read it from any book, on Linux, or just Google it. You will find it out. What are Linux syscalls, what are Unix syscalls, and what are Windows syscalls corresponding to these APIs. The advantage of these APIs is the library implementation may change depending on the OS, but user level processes can use the same APIs irrespective of underneath OS. Okay. Now, important ones are, we'll discuss only few. Create, it will create a new file. When it's created new, of course it will have a new metadata. Metadata is nothing but data about the file, right? Okay, data about data is some control information about file. It's called metadata. Okay. All right. And linking is creating a hard link that we have already studied. Okay, unlinking is just reverse process, removing the link, and when the number of links to an inode becomes 0, then file can be deleted. That we have already studied, right? Okay, so number of hard links, if say 5, it means that 5 connections are open, and one connection or one process wants to delete this, then it will not be deleted until everyone until there is only one connection left out. And if that process wants to delete, only it can be deleted, right? Then make directory, remove directory. Okay, open file that we have discussed by now. When we open, we get a file descriptor. Okay, which can use to refer open file. Okay, and when it's opened, then file path parsing and permission checking happens. So it's done only once. Okay, whenever a file is opened, whether the process has a permission to use a file or not, that happens only at the time of file opening. So it's not repeated on each read and write operation. And then OS creates multiple data structures that we have already studied. Okay, and then of course file descriptor can be thought of as a reference to operating system per open file data structure. That operating system we use for managing processes access to the file. Basically, for each connection, we have a file descriptor, and subsequent operations on the file will be done using file descriptor. Okay, all right, and then of course we have close, and then we have read, write, and seek. These are the important ones. Of course, there are many more. You know, I think for file related APIs must be at least 30 or something, 20 plus. I don't remember it correctly, right? Seek is actually going into a random place, because file now is a sequence of bytes. When we seek, there's a file position, we say go to a certain place, right? This is basically for random access. Okay, that's all. To summarize, we have studied concept of file descriptor, file table entry or process control block, open file table, vnode or generic inode table. Generic inode table we use in Linux, while vnode terminology we use in Unix. Okay, then we have also studied the concept inode. Inode information is there about a file, resides in disk. Okay, when file is opened up, this information is brought into main memory in that vnode table, and this information keeps changing while file is open and is in use. Okay, then we have looked at very top level or abstract level character special files and block special files. And we also studied file namespace and concept of internal namespace. Okay, we have also looked at concept of mounting and unmounting and virtual file systems, and some APIs we have studied in very brief. Okay, any question?
Sir, is the seeking database or address based?
No, I don't understand. Seeking
Sir,
is always position. You are not searching. You are seeking. You are just going to a particular position. That's it.
oh,
It's a file position. No? Its name is file position. So file position is changing. Wherever you pointer move the pointer, see, you may want to read from a certain position, or you may write into certain file position, right? So you move the pointer there and then do the operation. Okay.
thank you, sir.
All right. Let me just stop record.